Good evening. Welcome to POOIA, Professional Organization of Iranian Americans in Atlanta. One of the missions of POOIA is to honor, pay tribute, as well as to learn from Iranian and American scholars, scientists, and dignitaries who have made a difference in the world. Tonight, we are privileged to have an eminent engineer and a leader in artificial intelligence as our guest speaker, namely Dr. Jim Crowder, for which I am truly indebted to our own distinguished scholar and a well-known computer scientist, Dr. Hamideh Arabnia, Professor Emeritus at UGA and POOIA board member, for having introduced him to us and also going to introduce him tonight. POOIA is an affiliate of Qanun or Persian Cultural Center and is a non-religious, non-political, and purely an independent organization. I have the honor of being the president of POOIA, which has a board of directors different from that of Qanun. The lectures are all in English so that our Iranian American generation 1.5 and 2, who unfortunately do not know Farsi, can benefit from them. POOIA works tirelessly to uphold the 3 pillars of its mission. Number 1, to provide an opportunity for Iranian American professionals to network and support each other. Number 2, to help the next generation of Iranian American professionals to succeed and prosper. Number 3, to promote a positive image and counter the negative media depiction of Iran and Iranian professionals. Please support POOIA by donating via POOIA.net. I have requested our dear friend, Dr. Hamideh Arabnia, a renowned professor emeritus at UGA and a POOIA board member, to introduce his long friend. He has graciously accepted this. Dr. Arabnia, we are grateful to you for all your monumental contributions to POOIA and having accepted to introduce Dr. Jim Crowder. Dr. Jim Crowder, on behalf of POOIA and Qanun, I would like to thank you and express my gratitude to you for having accepted to talk for POOIA tonight. And Dr. Arabnia, I would appreciate it if you start your introduction of our eminent scholar, Dr. Jim Crowder. Please, we are all
Thank you. Thank you, Dr. Varzegar. Dr. Jim Crowder is an engineering fellow at Cobham Advanced Electronics Solutions, Advanced Program Development. Formerly, the company, formerly he was at Colorado Engineering Incorporation. Dr. Crowder's career spans over 37 years of experience in engineering, 30 of which has been in artificial intelligence. Having fielded his first neural network system in 1993 and his first fuzzy system in 1995, advanced computing and artificial intelligence has been his focus across Lockheed Martin, Northrop Grumman, Raytheon Technologies, and now an engineering firm in Colorado Springs, CAES. Dr. Crowder holds a PhD in electrical engineering, 2 master's degrees, 1 in electrical engineering and 1 in applied mathematics, and a BS in electrical engineering. He has designed and fielded multiple artificial intelligence systems for most of the Department of Defense agencies, including DARPA, Air Force Research Labs, the Navy, and the Army. He has published 8 books on systems, well, now 9 books. He has published 9 books on systems engineering and artificial intelligence through Springer, which are currently used by multiple universities as textbooks. Dr. Crowder has over 120 journal and conference publications and continues to be a leader in the field of artificial intelligence, evolutionary algorithms, fuzzy systems, cognitive architectures, and machine learning. His groundbreaking work in artificial psychology, which is the psychology of artificial intelligence, has been downloaded and read over 17,000 times and continues to be a major download from ResearchGate with close to 100 downloads weekly. He has begun work on his next textbook on artificial emotions and ethics for AI systems. Thank you so very much, Jim, for accepting our invitation. I'm honored to have you as a friend. We can start the talk now.
Thank you so much.
While he's doing this, I should also point out that Jim is really also a practitioner. He builds robots and on a daily basis, his robots learn, his robots live with him at home. So when I get to see him, he tells me how angry the robot was today and so on. And that to me is just so interesting because he tries to implement emotions into them. Okay, here you are.
So I appreciate you allowing me to talk to you tonight. One of the things that I tried to do, knowing that you're not all artificial intelligence engineers in the field, I wanted to spend some time talking about what AI is and is not, because the world gets incorrect views of artificial intelligence completely. So the top part of the diagram is what I find people think AI is, which is magic. Most people don't understand the science behind it. They're frightened by Hollywood has made people frightened of artificial intelligence, which they don't need to be. I know you've had people like Elon Musk and Stephen Hawking give warnings about AI. And while I take their input seriously, they haven't been in the middle of 30 years of how to develop algorithms and what cognitive means and how do we do that. So I want to take us through what actually machine learning and artificial intelligence means. What is the science behind it? What are the things that are important? Because again, even people in the industry miss so much of what AI is and is not. In fact, I'll start with 99% of everything that people call artificial intelligence is not. It's what I call virtual intelligence. They want things that learn and think and reason like people, but they want them predictable. Real AI is not predictable. I give the example of when I tell my VI car to take me to the dentist, it takes me to the dentist. When I tell my AI car to take me to the dentist, it might say, no, it's a nice day, we're going to the mountains. So let me start. Machine learning, and most people don't understand what machine learning is. Machine learning is mostly a data classifier. I teach it to recognize objects, then it tells me if it saw that object. That's really what machine learning boils down to. And how well it does depends on how well you provided information. Let me give you an example, then we'll jump into this. DARPA spent $18 million in a year training a system to recognize wolves in the wild so they can keep track of how many wolves there are. An entire year training it. First in operation, it saw a picture of a snow squirrel and called it a wolf. And what they found after a year of burrowing into it was every picture they trained it on that had a wolf in it had snow in it. So it learned to key on snow, not wolves. So when it saw a snow squirrel in a background of snow, it calls it a wolf. And that's where we're going to start, is talking about the data aspects of machine learning and artificial intelligence. As my dear colleague and friend, Dr. Carbone says, data without context is just ones and zeros. Unless we understand the data, we know what data to use, how often it's been used, its context. How good is the data good for? Is it in the right format? What was it taken for? We have this thing where we go out to databases and pull in data and use that to analyze it and make decisions, not understanding the context that each piece of data from each different database, the context in which it was taken, and how it was used and how it should be used. So the whole first part of machine learning and artificial intelligence is data selection. What data is available? What data makes sense? What data can be removed? In our human senses, our sensory memory throws out about 95% of all data it takes in. Video, audio, visual, everything. It throws about 95% of it away and keeps only what's relevant. But what's relevant changes depending on the context the person is in. If I'm in a car and I'm heading toward a bridge embankment, what's important is different than if I'm on the beach with my family. So the next piece we need to worry about when we start selecting data is it in the right format? I can get data from 100 different sources in 100 different formats. If we get it from a database, then we have to be sure it's not in a proprietary format. Data becomes important. If I give the wrong data to a machine learning algorithm, it'll learn on it. Just like ChatGPT. Let me say a few words about that and those chatbots. I wrote the book on chatbots, which is coming out beginning of next month, because there's nothing wrong with ChatGPT. It's how we use it. ChatGPT is a large language model. It goes out on the web and scrapes data and learns from it. So when you ask ChatGPT a question, it figures out what the most probable answer the web would have given you, and it gives it to you. It doesn't say what's truth. It doesn't say what's correct. It says what's the most probable answer, and that's what it gives you. ChatGPT, Bard, all of them have no understanding of truth, correctness. They just know what they've learned. So once we have data, we put it in the right format. We may find we don't have enough data. Another major piece of machine learning and artificial intelligence is synthesizing data. We find we don't have enough data. You've all heard of a deep neural network, yes? To train a deep neural network takes tens of thousands of data samples. Pick one subject that you have tens of thousands of valid data samples to train the network on, and the answer is there is none. So we try to take what data we have and use it to synthesize more data, because there wasn't enough data, or we have poor data. We move the data around, we change the background, we replicate it and fuzzify it and add noise to it and do all kinds of things to try and take a small data set and make it a large data set. And that has advantages and it has disadvantages. The disadvantage is I'm still not training it on a diverse set of data. If I want to train it on how to recognize a chair, I feed it tens of thousands of different chairs, not 3 chairs replicated 10,000 times. So part of the problem with data synthesis and data in general is data bias. You find that the machine learning algorithms and facial recognition that police forces use tend to identify Caucasian people better than African American or Latino, because they've trained the networks with more samples of Caucasian than they have of the other, which builds in an implied bias. It's almost impossible to build a machine learning system that has no bias. One of the things I talk about in the book is if you ask ChatGPT if it has bias, it'll tell you it doesn't. It's neutral. I had somebody I know ask it to write poetry, and he discovered instantly that ChatGPT is a huge bias. He asked him to write a poem about J. Edgar Hoover and write a poem about Malcolm X. And he wrote a glowing, amazing poem about Malcolm X and wrote this really nasty, scathing poem about J. Edgar Hoover. There's bias built into everything. As scientists, that's the thing that we struggle with the most, is making sure there's no bias. Here's an interesting question to think about. Can you have a thought that you can relate so unambiguously to another person that they cannot misinterpret your thought? Take some time to think about that. So, by the way, I know we're leaving time at the end for questions, but if you have any questions that you really want to ask, you can go ahead and ask them.
At the end, Dr. Crowder.
So, inconsistencies encountered in replicating complex data can lead to bias. It can lead to incorrect characterizations. Again, all machine learning is data classification. And the quality of data the quality of data we use to train it determines the quality of the data identification and characterization. The next thing is data exploration. We take in data, we analyze the data, we tag the data. One of the biggest problems with machine learning is I have to have data sets that I've tagged objects that I need to train on. You think about 10,000 data sets, and somebody's got to set and tag all 10,000 of them. That's why data synthesis is used so often, because the labor intensity. You'll find China is a good example. They take tens of thousands of people and pay them to daily sit and just tag data. That's their entire job. They get paid to do it 8-10 hours a day, thousands and thousands of them, because tag data becomes ultimately important in machine learning. So, understanding data and the data variables becomes extremely important. You have to see if I have outliers in the data that you need to get rid of. I need to look for patterns and relationships in the data to make sure there's not bias in the data, to make sure I'm getting a clean set of data. If I feed it all of one kind of data, the machine learning is going to just recognize that one kind of object. You've got companies that are spending tens of billions of dollars to figure out ways to thwart machine learning recognition algorithms. You'll see particular kinds of paint. There's a company now that makes clothing that screws up facial recognition software because it's randomly colored. If you wear that shirt, it screws up the pattern recognition and it can't recognize people. Another problem we have, which I talk about in the book, is now in the world of fluid genders, it's really hard for machine learning algorithms and facial recognition to determine non-gender specific people, gender neutral, transgender becomes extremely hard to pick out and accurately tag. Now, every time we use data, again, the question we ought to ask ourselves is, where did that data come from? Under what context was it used? What context do I need it? And what question am I asking it to answer? Data without a question is just raw ones and zeros. I have to ask a question about the data. I have to understand the question that data was trying to answer, why it was taken. The language you use might be important. R and Python are very common languages for doing neural networks, for doing language models, for doing machine learning. You can now buy, matter of fact, people are now using ChatGPT to generate code for them. That's nice, except whose code is it giving you? It's giving you code based on what it's learned. And there's no guarantee the code is correct. It's just the most probable code that it can find. So, outliers. That becomes important, again, if you're training a data set and you've got outliers in the data that don't represent what you're trying to train the network on, you're going to find it's going to, false alarm rate or false positive rate is going to go up. Hypothesis testing becomes important. In cognitive systems, we use hypothesis-based systems. If I'm trying to do management of a system and handle different situations, and I see data that I observe, I should look at a number of different possibilities for how that data was generated and what it means. So I create hypotheses. Then I look for data that supports and rebuts the hypotheses until I come to a level of acceptance that I can live with and make a decision. We talked about this. Yeah, it's interesting. It's 3% of data that we take in meets the quality standards we need for machine learning. Dealing with dirty data, incomplete data, and data that's of the wrong context cost companies about $3 trillion a year in the US. And causes immense amount of problems. Well, for misdiagnosis, for mischaracterization, misclassification of people, places, things. Again, for machine learning, a data decision is only as good as the data that was used on it. If you've got a business that relies on computer-generated data for your systems, and you can't guarantee I've got correct data, and you can't guarantee I'm going to create the right order or create the right mobile app. And again, companies cannot afford to waste time and energy correcting errors brought about by bad data. You find an example of bad data. Brand new attorney was trying his first civil case. Went out to ChatGPT. He was looking for case law that supported his defense for his client. He asked ChatGPT to find him case law that helped his cause, and ChatGPT came up with 3 cases, which he put in a brief and sent to the judge, not realizing they were made up. And none of those 3 cases actually existed. He was fined heavily and disbarred. So again, context and understanding our data, understanding what's correct data, understanding how we use it is crucial in artificial intelligence machine learning. Just like it's important in psychology, in computational mechanics, incorrect data can destroy a product or destroy an entire system. So the steps to go through that is to identify critical data fields. What kinds of data do we want? Are we sure we're gathering the right data? Are we putting it in the right format? Is it coming to us correctly? We have to collect the data. We have to go through the data and get rid of things that are copies of data, of outlier data, of incorrect data, of incomplete data, of imprecise data. All of that can come back to bite us. So once I have data, I've cleansed the data, I've gotten rid of the dirty data, I've gotten rid of the data that's not relevant. I have to normalize the data based on which algorithms I'm using. Every different kind of algorithms use different kinds of normalization, different aspects of the data. I've got to put it in a form that my algorithms can use. And it's not the same for every different kind of algorithm. If I'm using a convolution neural network, a Turing neural network, there are 10, 15 different kinds of neural networks. Each one needs data in a different format, different kinds of data, and does different things with the data. You may have to scale the data. You may have to normalize it to a t-test or a z-score normalization. One of those that becomes extremely important in how we normalize the data, how we get it ready to use. A great example, Mars probe, one of them that blew up. The data was put into the database in the Mars probe in British units, and it was taken out assuming it was in American units and destroyed the satellite when it got to Mars. So you had a several billion-dollar satellite travel all the way to Mars, and because nobody understood how to normalize the data correctly, nobody checked to make sure we're using the right units, destroyed a $6 billion project. It becomes extremely important to make sure we understand all parts of our system. For instance, if I'm using a fuzzy-based system, generally the data needs to be normalized between 0 and 1. If I'm using a different system, it would be normalized in a different scale. You've got this on record. I'm not going to go through the math, but just here are some of the things that people do to normalize data. Minimax is one, Z-norm normalization is another. I'll let you take a look at that at your leisure. One of the issues with normalizing data, like if I'm using it for a fuzzy system, and I'm normalizing it between 0 and 1, that basically is data compression. If I've got a range of data that's 0 to 100, and I normalize it 0 to 1, now I've got to be careful about the precision I use for the data, because I've compressed that data set 100 times. And you might lose a lot of important information if I take it, it was in, let's say, 4 or 5 digit precision, and I compress it 100 times. Now I've got to have more precise data because now I'm just between 0 and 1 when it was between 1 and 100. Now that I've done that, I've got to figure out what features the data has that I need. As I said, DARPA had an issue with, they assumed it was training and extracting the features of the wolf when it was actually extracting features of the snow. And it could tell you really well whether you've got a picture with snow in it. It just didn't know how to find wolves. Feature extraction is useful in selecting how I'm going to do the data classification. There are many different methods. One's called principal component analysis that's used to find which features in your data set are most useful. Again, let's go back to the human. We throw out 95% of all data we've taken in our eyes, ears, and sense of touch, because it's not relevant. Let me give you an example. If you can envision your house and the lawn and yourself sitting on the lawn, you see in your mind, you can see the lawn, but I guarantee you your mind didn't register and remember and memorize every blade of grass on that lawn that you sat on. And yet your brain recognizes there was a lawn and puts the lawn back together. That's something we have to be careful of with cognitive systems as we try to make them more and more useful, is what things are important. You may see a group on a platform. You've got a main speaker and 4 or 5 other people, and you're focused on the main speaker. But it turns out a year later that you needed to know who the guy on the end was. But your brain didn't save any of that data because it wasn't relevant to the context at that time. That's something we have to be careful of with machine learning and cognitive systems, is understand their context, understand we can't store everything. No system has an infinite amount of processing power, infinite amount of energy, or infinite amount of memory space. So we have to be careful how we gather data, how we store it, how we use it, what becomes important, and really make sure we're gathering those features that make sense that we can use later. One of the things we have to be careful of is meaningless features. As I said, the example of DARPA, they spent so much money and got nothing out of it because they didn't understand that their system was keying on the features in the snow and not features of wool. So that kind of model accuracy becomes extremely important. Here's an example of doing feature extraction where it takes all the features, it bangs them against the algorithm and finds which ones make most sense. Then you can figure out which features. I can't use all the features because I don't have enough processing power memory, but I can use the ones that are most important. So understanding which drive the system the most are the ones that you need to be careful of and use. Clustering is another way to figure out data that applies to other data. One of the things that Dr. Carbone, my colleague, and I, which Hamid knows well, is we adapted Newton's gravitational theory to information theory. So you'll use it to figure out what data is close to what data corresponds to, rather than the standard clustering, like nearest neighbor k-means. We use gravitational theory and apply it to information to help us understand what information belongs together. And any of this, if you're interested, get me your email and I'll send you papers that we published on all of this stuff. Now, if I have data, I've cleansed it, I've scaled it, I've formatted it, it's ready to go. The next piece that's most important is which machine learning algorithm should I use? Because they're not all the same. They have advantages, disadvantages for different kinds of information. Everybody's probably heard of a convolution neural network. That's the big thing now. Deep learning with convolution neural networks. everybody goes to convolutional network first, not understanding that it's useful for some things, but it's not useful for everything. There is no magic bullet. There is no one algorithm that's good for everything. And a lot of it depends on the kind of parameters, the kinds of features you're trying to learn on. One that we use a lot is called a cascade correlation network. Part of the problem is I train a neural network, I put it in the field, and it's immediately wrong because real-time environments change over time. And when something doesn't work right, I got to stop, I got to come back, I got to retrain the model for months, then put it back out in the field, and it's immediately wrong again because the environment's changing. Cascade correlation neural network can add internal layers on the fly as it learns, as it sees new data. It'll adapt itself to the data and to its environment so that I can run it real time. DARPA's put out several $1 billion for what they call anytime learning. Because, again, learning tends to be very static. And I need a system that continually learns and adapts. But standard neural networks don't function well for that. So we need to rethink and look at different kinds of neural networks. One of the things we've done is we build the networks one layer at a time. One visible layer, one hidden layer. Then that hidden layer becomes the visible layer for the next hidden layer. You do that several times, and you extract the feature set from each layer as you do that, so you know what features your network's training on. Then when it gives you an answer, you know why it gave you that answer. You know what features it was looking at in order to make a decision that I find this kind of truck, or I find this person, or I find this beach I'm looking for. And it's always good to try several different neural network algorithms, different machine learning algorithms, because it may not be obvious which one is better for different kinds of data. Or you may run them in parallel and then have a routine that scores them and picks the one that's most likely. That's another common way of doing it. That comes down to explainability. So how do I know why my system's working the way it is? I trained it, but I don't know what it learned on. As I said, it becomes extremely important to understand when I'm building machine learning, I'm building AI systems. Another thing that becomes important in cognitive systems is I have to pick a cognition model. I go back to psychology and look at all the different kinds of cognition models. One of them I use a lot is called the Rasmussen cognition model. Again, I published a number of things on that, but you got to pick out a cognition model, and each type of system I'm building, each type of data I'm learning on, each type of object that I want the network to recognize requires a different cognition model, a different neural network algorithm, different data formatting. All of that becomes important and critical to having a system that functions as efficiently as possible. Part of the problem is people just grab a network, train it, and run it, and assume it's going to give them good answers, and assume the answers they're getting are valid, and many times they're not, and can cause havoc with a system. Another thing is to understand, I'm going to take my data and you use part of it to train the system, part of it to test the system, and part of it to run the system. Understanding how much data I train on, how much data I test with becomes extremely important. And again, there's the difference between the system functioning well or the system functioning very badly. And unfortunately, we have a lot of badly done systems. What time is it?
8:10. For
Okay.
us, it's 8:10.
All right, so I've got about 10 more minutes.
Yeah, you have 20 minutes.
So once I have data, once I validated the data, once I picked out which algorithm I think is the best for my data, now I have to train the models. It's the primary step in machine learning. It's what machine learning is good for. I tell it, here are tens of thousands or hundreds of examples of things I want you to learn about. And then I want you to tell me if you see it again. So I've got to validate it, I've got to test it. And it's always good to use things that are outliers to see if you can fool the system. If I give it things that it's not supposed to recognize and it recognizes them, that means it hasn't been trained well enough. It's always important to test a machine learning system extensively with good data and bad data. I always run my system with just noise to see if it thinks it found objects that didn't exist. And I have found it to do that now and then. So how we train it, the data we use to train it, the data we use to test it becomes extremely important. Here's an example. When I was working at Raytheon, we had an innovation week every year. We'd all come down and try to build new ideas. We had a group that came down with a deep neural network. They guaranteed it could recognize 43 different weapon systems with 100% accuracy. I took their model and added 0.1% Poisson noise to it, and it then identified all 47 as an ostrich. Because they had assumed the noise model, and in real life, noise models are never what we assume. So it requires a systematic approach to making sure we get the data, get it correct, and that I can repeat the training, I can repeat the characterization, running it against many, many different data sets and making sure the answers are repeatable. Running the same data set through it 15, 20 times, making sure it gives me the same answer. I've seen that happen where it gives you different answers at different times. And again, if you're depending on that, if I'm in my car and I'm depending on the neural network that's trained to not run into a tree, I'm going to trust it. If it wasn't trained correctly, it might assume the tree is something you're supposed to go hit. Here's another example. Elon Musk, they spent an entire year training the neural network for a self-driving car. First thing did was run over a person, run over a robot. At the Computer Electronics Show 3 years ago, there was a Japanese company that had some autonomous robots, and they had it wandering down the street, and it did something it wasn't supposed to. It wandered into the street and was run over by a self-driving car. Why? I guarantee in that year of long training, nobody ever gave it to try to avoid robots. And what's interesting is the person it hit wasn't a mistake. Again, there's modules built in to determine what's the least damage. And if the least damage is taking you out, that's what it's going to do. So in self-driving car, here's an example. Somebody write me a use case for every stupid thing a person can do. You can't do it. So you just got to take and train it as well as you can. So generally, when we take data for training and testing, we train it on 70%, we test it on 20%. And then we put it in the field and see what happens. I talked about evaluation. So I've got a neural network now. I've got machine learning. I've tested it, I've trained it, and I'm putting it in the field. What are the interesting challenges with machine learning? Again, we talked about lack of transparency. Once I train it and I put it into a system, I feed it data, it gives me answers. I have no idea why it gave me that answer. I assume the answer is correct, but I don't know why it's correct. I may have something that relies on stochastic algorithms that don't produce the same model every time. I need to generalize them. I may not understand if I've covered all the cases. I give it, say, 1,000 different data sets, and then the data it sees in the field has the 1,001st example. So it's, you never know whether you've covered all the cases that machine learning is supposed to recognize. If I'm trying to recognize beach balls, have I given it examples of every beach ball? Or there's some that I forgot? The other thing to understand is there's no free lunch. Machine learning takes a lot of time, a lot of resources. It's very time intensive. Tagging the data can take weeks and months. Training can take months or years. Do it right, particularly for a deep learning network. I am skeptical of anybody that tells me they've adequately trained a deep learning network. Because again, training it correctly takes thousands of tagged data sets. And there's almost no subject in the world that you can go out and grab 10,000 valid examples. So most of all deep learning networks utilize some synthesized data, which makes them prone to problems. So those kinds of issues, you might have low performance. The interpretation of the results is dubious at best. Understand we take in data, we train networks, we put them in the field, and every single time the environment I find myself in the real world in is different than the data I trained on. Mm-hmm. So you've got to be careful. We've got to watch for that. That's why it needs to be tested extensively to make sure that I've covered all the cases, make sure I've covered the edge cases, make sure I've covered everything, particularly for important systems like a self-driving car or self-driving semi. Those become extremely important. This just shows you, I take a data set, I split it into a training set, test set, and validation set. Then I use it to evaluate whether my training models are correct or not. So model retraining becomes important when I find that I didn't catch all the cases. It doesn't produce maybe a performance change, but it does add cases to it. Now I've covered more cases than I had before. Machine learning testing principles become important then. I've got to have stable performance. Again, it better tell me the same thing. If I feed it the same data, once it's trained, and I put it in the field, I better get the same answer. Yes, I found that item. If I get different answers, then I got to go back and retrain it. Maintaining proper interpretation, reproducibility, all these things become important to have a valid machine learning system. It's not magic. It requires a lot of work. And the industry as a whole doesn't treat it as carefully as they should. We talked about that. Talked about tuning. So, in the end, my purpose here was to just give you a brief overview of machine learning, particularly from people who aren't used to dealing with machine learning, who aren't in the field. They may think it's easy to get a hold of, it's easy to do, it's easy to buy some software, I can train a network and I can do all kinds of magical things with it. That's not the case. Again, machine learning, matter of fact, most of machine learning I call machine remembering. Because you're supposed to remember what a wolf looks like, what a person looks like. And it's not magic, it's just classification of data, remember it, based on what you're trained on. And training is only as good as the data. Data is only as good as whether I can find data, whether I can cleanse the data, whether I can format it correctly, whether I can scale it correctly. All those things become critical to a machine learning system that's valid.